Okay, there we go. So the first rule, most important rule, is identifying the correct longest chain. Then the lowest numbering system. The lowest numbering system may be different depending on the functional group. If you have a functional group that needs to get the lowest number, if there aren't any functional groups, then it's simply the substituent that gets the lowest number. And then once you do that, you're left with all the things that aren't included in the branch, which is, or in the root name, in the chain that you've identified as the longest chain. So then you have to name all the substituents. So as far as naming halogens, it's just halo, which just means depending on the halogen, that would be chloro, fluoro, bromo, iodo, and that's it. Those are the halogens that we'll discuss here. So if we look at this molecule, it's an alkene, first of all, because we have a carbon-carbon double bond. We have a bromo somewhere. And the interesting thing about halogens is they can never be a part of the root name. For instance, there's no, they're always going to be a prefix. They're always going to be bromo or chloro. They're always halo. They're not going to be a part of like butane or pentane, like we have with alkenes and alkynes, etc. Halogens are never going to be like that. So we know right away that this will be a substituent, and then we have to look what's our longest chain. So we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6 rather, or starting here or up here doesn't make a difference. It would be 5, 6 in either case. So the only reason, why do we have to go this way instead of right to left? Why do we have to go left to right instead of right to left? It's because the alkene, which is our priority here for our second rule, needs to have the lowest number that it can, which in this case it is 2. Whereas if we go the right to left, it would be at 1, 2, 3, 4. So 4 is greater than 2. So as far as rule number 2 is concerned here with our lowest numbering system, it has to be left to right. And like I said, you could start at the top methyl or the bottom methyl. It doesn't matter as long as it's on the left. That's the important part. So, and then we have the carbon-carbon double bond, the alkene at the 2,3 carbon. So we would name what I've numbered as 2-hexene, or hex-2-ene if you smush the 2 between the X and the E. That indicates that there is an alkene at the 2 position. Hex is there's 6 carbons, so that's where this name comes from. And now we get to rule number 3 in our what I call the typical rules, and that is we have substituents left, right? So there's a methyl group at 2, so that's a 2-methyl, and there's a bromine at 3, so that's a 3-bromo as we've said before. And then when you put all this together, it's alphabetical order like we've seen before. So this would be 3-bromo, 2-methyl, 2, I'm running out of room, so I'm going to put this down here, hexene. But that's all one word essentially separated by hyphens. So you would submit this and you would think that you get 100% because you're right so far, but you're missing something that is important. Can this be cis or trans? And the answer in this case is it can't. So this is totally correct. But you have to be careful because if this is different, if these groups are different, then you have to consider cis or trans. And in this case, you should just use E and Z to be most comprehensive about this. In this case, since it's both methyls, this is an acceptable answer. If, like I'm saying, if we had something slightly different, let's add another substituent here. Let's just call it a bromine. Now these are different, the 2 groups on the left. So we'd have to prioritize and determine what is going to be, is it cis or trans, is it E or Z? So in this case, it would be Z because this group is has higher priority than the one here, and it's oriented up. So now over here, the bromine has higher priority than this propyl group. So this is the correct one. So this is cis, they're on the same side, which is Z. Remember Z for cis, it's the easiest way to remember it. So you would have to include this if it was relevant in your IUPAC name. In the one I gave as an example, it's not, but I want to mention it that you could get a challenging question where there's a chiral position, for instance, or this geometry, and you have to include that in the answer or it's wrong. So like, for instance, you could also have to determine if it's RS if you had, let's say you had this as a structure. If you don't tell me whether this chiral carbon here is R or S, then that's, you know, -1 or something. It's not the full answer because it could be R or it could be S. So you have to specify to be unambiguous, to be clear in what the structure is. So anyway, there's several examples in the worksheet for questions like this. So I don't want to spend too much recitation time doing them now, but here's the general scheme, and then you'll just have to apply it to the various questions that I have on the worksheet. So I'll pause if there are any questions. Otherwise, we'll move into the radical stuff, which is the more technical stuff in this chapter. All right, not seeing any questions. We'll move on to bond dissociation energy next, which seems unrelated to radicals and you know, basically the rest of the chapter, but it is how we predict which bonds will break and which bonds won't break in radical reactions. And their bond dissociation enthalpies is most accurate, but it's commonly referred to as energies as well. It's kind of understood that it's enthalpies if you say energies, but anyway, this is what you'll see in the textbook. So let's just look at a few representative cases. I got to pull up the data here. So if you look, for instance, CH3, so the bond dissociation energy of this is 370. I'll just compare a couple here to save time. So this methyl group, one of the hydrogens there is 405. And then we'll just do one more as a oops, this should be, aha, that's why it didn't make sense. This should be like that. And then this, like this. Okay, yeah, that makes sense. And this one should be higher, and it is, it's 440. Okay, so regardless, here's the raw data. You're not gonna need to have the data memorized. What you need to understand is the trend, and it's good to have the data to explain the trend. So, oops, sorry about that. So what bond dissociation energies or enthalpies are describing is a homolytic cleavage of the hydrogen, of this particular hydrogen bond. And I should, carbon hydrogen bond. I should be accurate here. We're talking about this one in this case. So first of all, homolytic cleavage is when one electron of each of that bond goes to each side of the bond. So you'll notice the half arrow means one electron instead of the double-headed arrow, which is 2 electrons. So what this makes is this and the hydrogen radical. So notice, I got a lot of questions about this on the homework. Formal charge association for radicals is the same as we've talked about before. You count lone electrons, which is like a radical, as however many there are. So if you consider this carbon, the radical counts as 1, and then it has 3 bonds, which are shared bonds, which by the normal rules count as 1 as well. So this carbon has 1, 2, 3, 4. You look at your periodic table, you'll see that you expect 4 valence electrons for it to be neutral. So this is neutral, which is why there's no charge here. And the hydrogen, the same thing. It's in group 1. You would expect it to have 1 electron to be neutral. It does, so the radical is neutral. Now, if you were to show this arrow with the double-headed arrow, that's completely different, because now you're lacking the radical entirely at that carbon. So it only has 3 bonds, so that's 3 electrons. So you'd have a positive charge there, which I did not draw that well, but there we go. Now you can see. So there's a positive charge on that carbon, and a lone pair on the hydrogen, which is a negatively charged now. So just this isn't related to the radical stuff, but you need to know the difference because it's just important. You need to know the difference between the double-headed arrow and the single-headed arrow and where the electrons are moving, and then how to predict the charge for your product. So anyway, it's a bit of a digression, but it's related. So what you're measuring here in the bond dissociation enthalpies is the amount of energy that's released when this bond cleaves in the manner that we see here. So these are always going to be a higher in energy than they were before. So you needed to input this energy to cause the break. So what we see is it's harder to break this bond than this one. So if we do the same radical reaction, we get this, and then the hydrogen atom, the radical. So this one is higher in energy because it's here. It takes that much energy in kcals per mole, but we're not really interested in that. Just it takes more energy than this, which is what we have here. Now the reason is why. Well, this can resonate, radical resonance, and make this resonance contributor. So this has a stabilization factor by resonance, which explains that. And this one just doesn't. However, this one takes less energy to break than this one because the radicals that are that have heavy substitution, like these methyl groups, are stabilized by induction from the methyl groups. So methyl groups are somewhat weakly electronegative, which means that they're slightly electropositive. So if you can think about it as having some amount of partial positive charges around, they can donate their electrons towards the stabilization of this. So the idea is higher substituted radicals are more stable than ones who aren't. So what that means is it's much easier to break this bond because there are 3 methyl groups than if there wasn't, which like there isn't in this case. There's only 2 methyl groups, so it's harder to break this bond, which is why we see a higher energy here, which in other words means that the products that are made here are more stable for this one as compared to this one. And this will predict the intermediates that form in all of these reactions and then you can explain why certain products are seen as a major product and others aren't. It's similar idea to carbocation stability that we've seen before. You want to be able to predict the product based on the intermediates that are formed. In this case, it's radical. In our alkene chemistry, it was the carbocation, but it's similar. The trend is the same. Like a tertiary carbocation is the most stable. A tertiary radical is more stable than secondary and then primary. Same with the allylic position. So that's the introduction. Now let's work through some actual examples of doing radical reactions and predicting products. But I'll pause again if there are any questions about this. All right. So now for the rest of the class, we will just look at various types of radical reactions and their mechanisms. So first of all, based on what we just said, which one of these is going to be the major product? A or B? What do you think? Here's A, here's B. Got a 50-50 chance. So if you just want to guess, that'd be okay. I don't know, B. It's actually A, and I'll explain why. So it's hard to know this if you don't understand the mechanism. So what we just learned from bond dissociation energy is that in this case, we have secondary carbon, right, and primary carbons. right? I just put 2 and 1. I should put the degree sign right to be most complete. So what I'm saying is if we form this intermediate or this intermediate, this one's secondary, this one's primary, so this is more stable. So now I'll show mechanistically here in a second. H nu is written under the arrow. That means energy. H nu is, H is Planck's constant and nu is the frequency of light. So usually it's just a UV light that's shine on your system to cause the radical initiation. Yep, so you might see this as HV too, just because it's most accurate to be H nu, but I've seen it as HV as well. So anyway, that's what it means. You might also just see heat. It doesn't have to be this, what I put. But you need some catalyst. If you just have bromine, it's not going to do this. You're not going to get these products. So mechanistically, this product A forms through this secondary radical. So that's why this is the major by far, because it's easier to make this intermediate than this one. But it's not impossible to make this one, just like our carbocations, the minor products sometimes can still form. It's not always so clear cut that it's only going to be one product. The radical reactions are especially troublesome with byproducts, as we'll see here in a minute. So any questions on that? So without getting into the mechanism, the takeaway here is that the halogen that you're adding through this radical reaction is going to add to the most substituted position. Is the 1 and 2 degree thing just referring to being connected? Yeah, it's primary, secondary, meaning primary means you're connected to 1 carbon group, secondary means you're connected to 2 carbon groups. Because they all have to be connected to 4 things, right? They have to be connected to 4 atoms, but the 1 and 2 is referring to the number of carbon groups specifically. So the takeaway here, I'll write it too, just to be deliberate here. So the halogen that's added will always add to the most substituted position. I should be more clear than that too, to the most carbon substituted position, because if it's substituted with like an oxygen or nitrogen stuff, the chemistry can get a little bit different, but you probably won't see that much here. So this is why we see the product that we see, because it's adding to the carbon that's substituted twice, the disubstituted carbon. Notice if it adds here, that's the same thing. So you can draw that also. That would be fine. It's the exact same molecule. All right, so let's just do one more like this, just to make sure that point was driven home. So if we have this and we have the exact same conditions, where is the bromine going to add? A carbon A, B, or C? What will be by far the most? B, yeah, exactly. Because B is substituted by 3 carbon groups. The others are, C is substituted by 2 and A is only substituted by 1. Good. So now let's explain mechanistically why that's so. So the radical mechanism is significantly more complicated, in my opinion, than the alkene and alkyne mechanisms that we've seen so far. This one, radical mechanisms have to be defined in 3 steps to explain the type of stuff that's happening, because homolytic cleavage like this, or like what we've already seen, this is not a natural process. It takes a lot of energy for that to occur. And if it doesn't occur, none of this chemistry is possible. So you need energy, and lots of it, So I'll just say energy input for this to happen. Because if homolytic cleavage like this was just occurring all the time, then radical reactions would just be running rampant and no compound would be stable. So the reason we can do this is because we can input a sufficient energy to initiate the process. So that's why the mechanism consists of an initiation step in which you create the radicals. Once you create the radicals, then it will all just, the mechanism will just proceed on its own and no more energy is required. So if we consider bromine, bromine's the most common to use for these kind of halogenation reactions. And if you input some energy, the initiation step is always going to be this homolytic cleavage of Br2, in which you create 2 bromine radicals. And I am omitting the lone pairs on bromine just for clarity. But remember that there are 6 electrons around each bromine in 3 lone pairs to fulfill the octet for bromine and for any X2 molecule. But usually they're not shown like that just to avoid, a million dots basically, but they're understood that they're there. So that has to be known when you work through these. Okay. So once the initiation step has occurred, then you'll have potentially a series of propagation steps. There's at least going to be 2, but there can be as much as like 20. You wouldn't have to recite like 20 on an exam or anything like that. But the point is that depending on the identity of your starting material, you could have a lot of propagation steps and a lot of craziness going on. So the initiation step, as the name suggests, creates the radicals because it's an initiation. And without the creation of the radicals, you don't have any of the next stuff happening. So the propagation steps begin to make the product. So a specific propagation step will make the product. So let's show this now. So this starts with the radical, bromine radical that we just created in the initiation step. And then it will react with your substrate, whatever your starting material was. So let's say that we had some alkane. I'll just say ethane for simplicity. So what is going to happen here is we're looking for the weakest bond. Well, the carbon-carbon bond is pretty strong, so that isn't the weakest bond, but all the other carbon-hydrogen bonds are the same. So as far as assessing the relative strength of these bonds, the carbon-hydrogen bonds are the weakest, and they're all the same. So I'm just going to pick this one for ease of drawing. So we use the 1 electron from the radical here, and then we have a homolytic cleavage, again, between this carbon-hydrogen bond, where 1 electron from this bond creates a new bond between the bromine and the hydrogen, because now we have 1 electron and 1 electron, that's 2. So that's in essence a bond like that. Then the other electron in this bond gets cleaved onto the carbon. So you end up with this hydrogen bromine bond creation and the formation of this new radical. This one, where this 1 electron that's here is from that bond that's cleaved, like is strong. Okay. Then you have another propagation step where this radical that you created, the carbon radical, can react with the Br2 as in its diatomic state, its molecular state. So that is like this. And now this bromine-bromine bond is relatively weak when exposed to a radical. So that's why once this initiation has occurred, this is always going to just proceed very quickly. So now this homolytic cleavage of the bromine-bromine bond occurs. You create a carbon-bromine bond like this, and then the other bromine becomes a radical. And notice that this will be our product, the brominated haloalkane. In this case, it's bromoethane. So in this simple mechanism, I didn't want to overcomplicate it by making the alkane particularly difficult. But if it's not ethane like this, the radical will form at the most substituted position. Here, they're the same, so it'll happen at either one. But if you had something like this, then the radical is going to form there in the most amount. Excuse me. So that's all the propagation steps for this, for ethane, because there's only these two positions. But if you could make more radicals, then it would, and there would be more propagation steps. So now the last set of stuff, or last set of steps, is a termination step. And that is where you have two radicals reacting together to, it's why it's called termination, to stop any more radical formation. And once that happens enough, you will stop, there will be no more radicals left, and you won't have this reaction continuing anymore. So questions on this, because I need to erase because I'm just out of room. But so higher energy increases the probability of creating radicals. Yeah, exactly. If you didn't have a high energy state, it's not going to occur. But if you mean, so we have to be clear here, because if you mean higher bond dissociation energies, then it's the opposite. The lower the bond dissociation energy, the easier the radical will form, because the bond dissociation energy is a measure of the energy that you need to input to break the bond. So the higher that is, the harder it is to break that bond. Okay, great. Yeah, because here's one other way of thinking about it, just very quickly. There is an input of energy that's required, right, to get to any transition state. So the bond dissociation energy, you can think of it as somewhat of a measure of how much energy you need to get to that state. So if there's a lower one, then it's easier to reach that. And that's another way of thinking about why the lower the bond dissociation energy, the easier it is to form that product or make the radicals. Okay, now, so last thing about propagation steps, it always involves one radical and one non-radical. So radical and non-radical as reactants, and then it forms a new radical and a new non-radical product. All right, so I'll just say new rad and then new compound. So the initiation step goes from a non-radical compound to two radicals. All right, so now the termination steps are the opposite of initiation, which makes sense, right? Based on what the words mean. So termination steps takes two radicals and forms a new compound, non-radical compound. And by new, I just mean not what the radicals were, because this could be a reoccurring thing where you regenerate like a starting material, for instance. So in our case, the most obvious termination step is you could take the two bromine radicals and reform molecular bromine, Br2. And notice this is the exact opposite of the initiation step. That's one possibility. This doesn't happen a lot because it's very unlikely when you cleave this bond that the bromines are going to be near each other to initiate, to just be in the proximity to create this bond. So this happens, but not in significant quantities, usually. But then you also have the ethane radical which can react with a bromine radical to make the product. This is a termination step that makes the product. So the propagation step also made the product. So that's why to show a complete mechanism for radical reactions, you need to show all of the propagation steps and the termination steps. So usually on an exam, the question will ask for a particular step just because it takes like 15 minutes to write an entirety of a radical reaction, which, you know, it's just not practical on an exam. But a lot of times students miss that type of question because they don't have a good grasp of just looking at it and then what type of step there are. So always termination, if that's what's asked, you better take two radicals together to form a non-radical. If it's propagation, you have one radical, one non-radical, and then you make a new radical and a new non-radical. And if it's initiation, it's the opposite of termination. You have a compound making two radicals. So now, is there other radicals in our system, right? We have bromine and CH3 in the carbon radical. So we can also have two carbon radicals react instead of having two bromine radicals react. Right? So you could get this happening. And now you just make a longer that's bound to it, but I'm out of space. But you make butane. This is butane. So you went from ethane to butane. This doesn't happen a lot. But again, this is why radical reactions are kind of a mess, both to teach and to actually like do in the lab, because you're making a bunch of byproducts that you don't want. And as a matter of fact, this isn't even the only possibility. You could also have the radical, the carbon radical, react with the well, this is going to be a propagation step, right? No, it's not. So you could have it react with this position. This one is, if I had to guess, this is almost certainly not going to be included, but just to be complete, if this happens, you create a bond between the carbon and hydrogen, and then you have a homolytic cleavage onto this carbon, which you can also put directly to this bond, and then use this one to put directly to that bond, and then you would make CH2CH2, or the ethene, the alkene with two carbons, and you make ethane back because you created this carbon hydrogen bond, which now is CH3CH2 plus another hydrogen is CH3, and at the same time you created this carbon-carbon double bond. So that's another possibility. But the point of showing this is that there's a bunch of termination steps, and there may even be more that I'm not thinking of for this particular example. So again, on exam questions, if they want a termination step, they will usually tell you, show a termination step that makes, you know, this. They'll tell you that it makes ethene, show me how you mechanistically how you made that, how that could come about. So anyway, that is radical mechanisms in brief. Any questions on this? So how do we know what molecule is majority? So like, do you mean product, the major product formation? Yeah. So it is whatever's the most stable radical intermediate will give the major product. So I'll answer your question with the next example, like specifically. So for instance, let's say we have this reacting with Br2. Again, Br2 is the favorite. So once you get good enough at these, you can just memorize. I'm not a big fan of memorizing because I forget stuff. But for an exam, if you have a great memory, you can memorize it or look at the mechanistic approach that I'm giving as an alternative. So to make either of these, you have to go through either this intermediate or this intermediate. And I should have drew them under each other, but this intermediate will make that when it reacts with Br radical or just Br2, remember, as the propagation steps that we just saw, or the termination step, depending on what it's reacting with. Same thing here. So now to predict which one is seen in most quantities as a major product, it has to do with the stability of this. So is A more stable or is B more stable? And briefly why? Yeah, A, more carbon bonds. So this is the major product for the reason that you gave. And that's how you would predict it based on the mechanism. So this type of stuff, if this is more your question, I'm thinking about it more. Does this happen? Yes, but this is always going to be minor. Any two alkane radicals or carbon radicals reacting there's never going to be as much of that, because remember, the initiation step is forming bromine radicals. So the bromine radicals are going to be the most available species that are radicals. So anything else that's not a bromine reacting with a radical is happening as a small aside. It's not the main reaction. Okay, does that answer the question? All right, great. Any other questions? There are other types of radical reactions that we'll talk about next. This is basic halogenation, but it doesn't have to be an alkane starting material. It can be something else. All right, so getting to what I was alluding to there, you can have allylic bromination, which is this, where NBS is N-bromosuccinimide, which don't recall the structure for sure, but it has this nitrogen bromine bond. I'm not sure of the identity of all of this parts, but it's unrelated. It's not, I mean, it's related, I shouldn't say that, but it's not critical for the mechanism. You just know that you create a bromine radical that reacts with a radical formed at the allylic position. Because remember, allylic radicals are stable. So out of our options here, vinyl radicals are not stable. So this is where the radical will form in most quantities. That'll react with this and make the product. It doesn't react with Br2 because remember, the alkene can react with Br2 to make the dibromo at the alkene. So if you don't have NBS, you'll get this product. So that's why you do this with NBS instead of Br2. So that gives you the allylic bromination. So remember, allylic positions are the carbons adjacent to the double bond. So here's the double bond. This position is allylic. That's why this is called allylic bromination. This position is called vinylic, which is the carbon-carbon double bond, the carbons in the double bond themselves. And the mechanism is essentially the same that we just talked about, and we don't really have time to go through an entire example, but the point is it adds allylically. So now I'll give you a harder question about this. So what's going to be the major product? A or B? Or maybe better question to start with, what positions are allylic? So of the ones labeled with the lowercase, which ones are allylic? A is allylic. Are there any other allylic positions? A is not the only allylic. C and B. Yep. A, B, and C. So to assess this question, you have to know which position is most stable. And they're the same, right? They're all allylic. So there's no preference there. The only difference that will predict a major product is the amount that you can form. So since there are two positions here that are identical, you can form this twice when you only form this once. So B is our major product, but probably it's only like 60%. You know, if you do the direct statistics, usually the chemistry products don't come out to be directly like the statistics would predict. But if in these three options, 2/3 of them make this, 1/3 of them make the other one. So you would expect this to be 66%. I'm sure there'll be some deviation with experimental limitations. So this will probably be 60% and this will be 40%. But on an exam, you would be expected to draw both of these because they're both going to form in a significant amount. Like 60-40 is a significant mixture. So both of these will form. And the reason that this is hard is you just have to recognize that these are still allylic, even though we like to think of an allylic position as just this moiety, but you can have stuff attached to the other side that's also allylic. So that's the challenge of this question, I guess. So good that those would be, both of those would form. B, if the question was what's the major, I would say that B is a major by a small margin. Okay, now we only have a short time left. So now let's talk about, you can have anti-Makarnikov additions to a double bond by using these radical mechanisms, which is the last thing we'll talk about. Give me 1 second. Right. So we have seen this before in chapter 6, I believe, where we make this. Right. This is, you make the intermediate, that is this one, and then you add the bromine to that position, to the carbon, and you get here. So it's possible, this is Makarnikov, oops, sorry, you couldn't see that very well. So this is Makarnikov addition, but if you do the same thing with a radical initiator, like peroxides, you would get the anti-Makarnikov addition, which 1, 2, 3, 4 is here, because of the radical mechanism, because you're making a more stable radical by this process. So let's look at the mechanism very briefly. I'm not going to go into the entirety of it, but the initiation step involves the cleavage of an oxygen-oxygen bond, which is extremely weak bond. So you'd make RO, you make 2 of them. Then this can react with HBr and make an alcohol and the bromine radical. So this makes ROH and the bromine radical. And then the bromine radical can react with this position. It reacts here. So you have to think about this. So if this is going to bond to the double bond, so this is not how it would go. I don't think it will go like this, actually. It takes this position, you get HBr. Yeah, this makes much more sense. So then you get here, vinylic position. Actually, I was right the first time. Apologize for this. So here's one point, and this is why I realized I was right the first time, is pi bonds themselves, you'll get this from bond dissociation energy. Pi bonds alone are weaker than sigma bonds. We know that double bonds are stronger than single bonds, but the pi bond is this bond specifically, not the entirety of both of them. So the additional stabilization from the pi bond is less than a whole other sigma bond. So when that happens, this can cleave. And if this just cleaves, like I've shown here, that would make a tertiary position, tertiary radical, and then a primary one. But if we react this position with a radical, then you would get only the tertiary radical, which is what happens here. So this would make a bond between this carbon and this bromine, which is here. And we still have the two hydrogens that were there initially. And now this radical. So if it was going the other way, like I was showing and then realized it's wrong, you would make this, or if you use the double bond and have it add here, you would make this, which is both of those are worse or less stable than this intermediate. Then you can have this get quenched with HBr. Like this, reform the radical, and then so you would get the anti-Makarnikov product, and you reform bromine radical, which can then react again with another equivalent of the starting material, the starting alkene. So this mechanism is probably, again, probably not going to be shown on the exam, but you need to know that this condition makes the anti-Makarnikov. The mechanism is the reason why. So again, I think it's good to know it, but you probably aren't going to be quizzed on that particular detail just because it's a technical piece. But you'll have to know that these conditions make the anti-Makarnikov, which is, in other words, when the bromine adds at the less substituted carbon. So that is all I have. If there are any questions, I'll be happy to stick around for a minute too. But if not, hope you guys have a good day. I'll be posting again on YouTube in a few, by the end of the weekend. I've had a lot of other things that I needed to get done. So I'll have some radical stuff prepared.